Hey, Luke Sharappa here. We're going to do some category theory. I'm going to show you my adjoint footballs. So suppose we have an adjunction, L is left adjoint to R, and categories and functors as shown here. Any adjunction comes with two natural transformations, eta, which goes from the identity on C to RL, and epsilon, which goes from LR to the identity on D. These have to satisfy the zig-zag identities. What are the zig-zag identities? Well, there's multiple ways you can sort of write them down. You could just write down an equation that says them, but equations are boring compared to diagrams, and diagrams look cool and are easier to generalize to other contexts, like maybe we wanted to change this from an adjunction in cat to some other two category, so we're going to try and do it in terms of diagrams. We could do string diagrams, which is where you sort of represent two-dimensional things by zero-dimensional things, and in general d-dimensional things by, in this case, 2 minus d-dimensional things, and then you get these pictures. This squiggle is equivalent to a straight line, and this straight line is equivalent to the sort of opposite squiggle. This is where the name zig-zag identities actually comes from, and this is cool, but not what this video is about, because there's another way, the sort of traditional way, where you just use the two-dimensional notation for natural transformations. Functors are still one-dimensional, categories are still points. As you might expect if you grow up seeing diagrams with, categories as points and functors as arrows, etc. So the issue with this one is really this. In an ordinary commutative triangle, we'll have basically two different maps. This is a map and this is a map. This map is drawn so that you can see how it factors through this object, whatever it is. But there's really two maps, and these two maps are equal. This is another commutative diagram. Here we're saying that these three maps are all equal. Any commutative diagram, except possibly some of the infinite ones, breaks down into basically saying something like this, that two dots, some number of arrows between them, they're all equal. So what if the arrows, here the arrows are one-dimensional, but what if they're two-dimensional? Then you can draw sort of one in some region on the paper, but if you want to draw the other, here's your one-dimensional source, one-dimensional target. If you want to draw the other, it would normally start at the source and end up at the target, and I don't know, maybe you could draw it in annulus like that, but it starts to look weird. Plus this inner circle is really maybe only one point because it all has to have it gets awkward. So what I suggest you should do is go into 3D space, and what we happen to have lying around in 3D space is in fact footballs. So this is a football, and it's got two halves. Each half is a certain natural transformation. The halves are two-dimensional. When I say half, I mean like just the surface. The inside of the football doesn't really exist. We're just talking about the surface here. So each half is a two-dimensional natural transformation, and it has a source here, which is one-dimensional, and a target here, which is also one-dimensional. The source and target also each have a source and target, which are the same. The fact that they're the same is not really a coincidence, but can't get distracted too much. One of the natural transformations is the identity on R, the right adjoint. This here we have is the right adjoint football. Arbitrary convention, I guess, because no one ever said what side an adjoint football is, but the right adjoint functor is on top of the right adjoint football, so I think it makes sense. In any case, this is the identity on R, natural transformation from R to itself, and this is the same as this other more complicated natural transformation from R to itself. Here we have some identity transformations sort of fit into there, but we also have eta and epsilon getting involved. This eta comes out here from the identity on C and goes to RL right here, and then epsilon scoops it up back into the identity on D. These identities, they're sort of hidden here, like you would expect maybe the identity to appear here so that eta could come from it, but the identity doesn't really matter. It's sort of, if you're familiar with the string diagrams, like normally, nominally, you might be supposed to be drawing something like this to represent the identity here and something like that, and similarly on the other one. But normally, you just leave it out because it's the identity. It doesn't really matter. It can come and go at will, and R composed with the identity is exactly R. So that's why they sort of, I guess, squish in or become concave in a slightly weird-looking way, I'll admit. So yeah, this is one composition that's the identity, and the other one is on the left adjoint football, which looks sort of like a mirror evil twin version of the right adjoint one. Heh, evil, not really. None of the categorical duality things are evil. It goes from L to L. This side is the identity on L. This side is eta and epsilon, again composed in a special way. So yeah, that's it. The zigzag identities put on footballs. If you want to learn about category theory, or even if you don't, I recommend you do. I've put some links in the description to where I learned about category theory and other resources that I think will help you to understand this video. Thanks for watching.